Hello everyone, welcome to Clean Copper Talks. So in today's video we are going to explore one of the most fascinating advancements in advanced oxidation process called Photo-Fenton process. We have already seen Fenton process in our previous video and this is a video series on advanced oxidation process. Now imagine if we could use sunlight itself to make wastewater treatment more efficient. Instead of relying only on chemicals, what if natural solar energy could be used to destroy toxic pollutants even faster? Sounds exciting, right? In this video, we will understand what Photo-Fenton process is, how it works, why it is better than conventional Fenton process, and its applications in India and around the world and the latest research development. So stay till the last. Before understanding Photo-Fenton, let's quickly recall the conventional Fenton process. In classical Fenton reaction, ferrous ions reacts with hydrogen peroxide to generate hydroxyl radicals. These hydroxyl radicals are among the strongest oxidizing agents known and can destroy a wide variety of organic pollutants. But researchers noticed something interesting. After some time, the active ferrous ion gets converted into ferric ion. Once this happens, the reaction slows down because there is less ferrous ion available to produce hydroxyl radical. This raised an important question. Can we continuously regenerate ferrous ion? Can sunlight be used as a free energy source to improve this process? And the answer is yes. This led to the development of photo-fendant process, where light energy continuously generates the catalyst and significantly improves pollutant degradation. So what are the limitations of classical Fenton process? Although the conventional Fenton process is highly active, it has several limitations. First, it generates a large amount of iron sludge, which requires proper disposal and increases operational cost. Second, fresh chemicals must be continuously added because the catalyst gradually becomes inactive. Third, catalyst deactivation reduces treatment efficiency over time. Another limitation is that hydroxyl radical production decreases as the ferrous ion is consumed. Finally, the process usually works best under acidic conditions, typically between pH of 2.5 to 3. These challenges encourage scientists to search for a more sustainable and efficient alternative. That's where Photo-Fenton technology comes into picture. Now let's understand the chemistry behind Photo-Fenton process. First, the reaction is exactly same as the conventional Fenton reaction. Ferrous ion reacts with hydrogen peroxide to produce hydroxyl radicals. These hydroxyl radicals attack pollutants and break them down into smaller compounds. However, during this reaction, ferrous ion gets oxidized into ferric ion. This is where light plays a crucial role. When ultraviolet or visible light strikes ferric ion, it converts back into ferrous ion. This regeneration helps catalytic cycle running continuously. As a result, more hydroxyl radicals are produced throughout the treatment process, leading to a faster and more complete degradation of contaminants. In simple words, sunlight acts like a catalyst booster that keeps the reaction alive. So why Photo-Fenton process is superior? The Photo-Fenton process performs better than a classical process. The biggest advantage is higher hydroxyl radical production. More radicals mean faster destruction of pollutants. Second, continuous regeneration of ferrous ion reduces catalyst loss and improves reaction efficiency. Third, Photo-Fenton achieves better mineralization. Instead of merely transforming pollutants into intermediate compounds, it converts many of them completely into carbon dioxide, water, and harmless inorganic ions. Another advantage is lower chemical consumption. Since the catalyst is continuously regenerated, hydrogen peroxide is utilized more efficiently. Perhaps the most exciting benefit is that solar energy can replace artificial ultraviolet lamps, making the process more sustainable and energy efficient. So the major variations of Photo-Fenton process are UV Photo-Fenton, solar Photo-Fenton, visible light Photo-Fenton, and LED Photo-Fenton. As the name suggests, these processes differ by the type of light energy which it uses fe- uh, to regenerate ferrous ion from ferric ions. Now, the applications in India. India receives abundant sunlight for most of the year. This makes photofenton technology particularly attractive for Indian conditions. One major application is textile wastewater treatment. The process effectively removes dyes, reduces color, and lowers chemical oxygen demand. Another important application is pharmaceutical wastewater treatment. It can degrade antibiotics and other persistent pharmaceutical compounds that are difficult to remove using conventional biological treatment. Several IITs, CSIR laboratories, and research institutes are already conducting pilot-scale studies on solar-assisted wastewater treatment. Looking ahead, Photofenton has tremendous potential for decentralized treatment systems, industrial water reuse, and even zero liquid discharge applications. What is this global stage scenario? Photofenton technology is already being implemented in several parts of the world. Spain is considered one of the global leaders in solar photofenton research. Large pilot plants have demonstrated successful municipal wastewater treatment using natural sunlight. Several Mediterranean countries have also adopted solar-assisted treatment because of higher solar intensity. Italy has focused on removing pharmaceutical contaminants using advanced oxidation technologies. Across the European Union, Photo-Fenton is being integrated into water reuse initiatives aimed at building a circular water economy. Even in remote communities across Latin America, solar wastewater treatment systems are proving low-cost solutions where electricity is limited. These examples show that Photo-Fenton is not just a laboratory technology, it is gradually moving towards real-world implementation. Research in Photo-Fenton technology is advancing rapidly. Scientists are developing modified catalysts that work efficiently under visible light and over a wider pH range. Nanomaterials are being incorporated to increase catalyst surface area and improve reaction efficiency. Researchers are also combining photofenton with membrane filtration, ozonation, and photocatalysis to create hybrid treatment systems with even higher removal efficiencies. One of the most exciting developments in the use of artificial intelligence. Machine learning algorithms can optimize reaction parameters such as pH, catalyst dosage, reaction time, and energy consumption. These innovations are making photofenton smarter, more efficient, and more suitable for large-scale industrial applications. So let's quickly summarize today's discussion. Photofenton process is an improved version of classical Fenton reaction. By using light energy, it continuously regenerates ferrous ion, resulting in higher hydroxyl radical production and a faster degradation of pollutants. Its major, its major advantage includes improved mineralization, lower chemical consumption, and the ability to use renewable solar energy. However, some challenges still remain. The process generally requires acidic conditions. Catalyst recovery can be difficult, large-scale implementation needs further optimization, and treatment efficiency depends on the light availability. Despite these challenges, photofenton represents one of the most promising green technologies for future wastewater treatment. As a renewable energy and water reuse becomes increasingly important worldwide, we can expect this technology to play a significant role in sustainable environmental engineering. Thank you so much for watching this video. I hope this explanation helped you to understand how sunlight can significantly improve wastewater treatment through photovoltaic process. If you found this video useful, please hit that like button, subscribe to the channel and share it with your friends and colleagues. In next video we will explore the exciting electrophoton process where electricity replaces light to continuously generate powerful oxidizing radicals. I'll see you in next video. Till then, tata, bye bye, take care.